Alright, so today we'll be looking at worksheet 1 of the force unit. These questions will generally be focused on the force diagrams and how to draw them. So I've assembled basically 3 types of questions on force diagrams that you'll see in these worksheets. So this is the first one. This says, draw a force diagram for the skater moving at constant speed across frictionless ice, label the forces, and use equality marks on the force vectors. Okay, so let's just do the most basic thing, draw a circle around the skater just so we know that what we're drawing the force diagram for. And then we have to figure out what the net force is. So it says here that the skater is moving at constant speed across frictionless ice. So when it's moving at constant speed, we know that acceleration is 0 because the velocity isn't changing. And since force equals mass times acceleration, and acceleration is 0, we know that the force itself is also 0. So the net force on the skater right now is 0. However, that doesn't mean that there aren't any forces acting on the skater. So we'll look at our most basic force, which is basically the easiest force to put down for any of these questions, which is force gravity, because there's always going to be a gravitational force on any object. So there's a force gravity that's pointing downward, because that's where the center of the earth is for the skater. It's pointing downward and is acting on the skater by earth. So let's just label that right ahead. And then second of all, well, it says net force is 0, right? So that means that there has to be an equal force in the opposite direction of force gravity. So usually that force would be the normal force, since there's no like pull or any kind of airlift acting on the skater that would cause the skater to move upward, except normal force. So that's going to be the equal and opposite force that we'll use to counter the force gravity. So draw an upward arrow for the normal force, and then we'll label it, well, it's normal force and it's acting on the skater by the ice, because the ice is the surface that the skater is traveling on, right? So now we have to do the equality markers. So I've already said that the force normal is equal and opposite force to the gravitational force. So we know that these two forces are equal just right off the bat because the net force is 0. So all I have to do is put our equality markers on force normal and force gravity to show that they're equal. And that's it. You're done for this question. So our next question is a little bit trickier because this time there will be a net force instead of having a net force of 0. So first of all, we just draw around the softball player to show what we're drawing our force diagram for, and then now we'll look at the net force. Well, generally for these questions, we'll find out where the net force is by looking at the motion of the object. So it says that the softball player is slowing down as she slides into the base. So if she's slowing down, then that means that, well, there is an acceleration, or rather a deceleration. But in this case, since she's slowing down, that's deceleration. That would be an acceleration that is in the opposite direction of her motion. So from the picture, we can tell that her motion is going towards the right, which means that her acceleration must be going towards the left. So for our net force, we'll just draw out leftward pointing arrow to represent the net force that is pointing towards the left to show the deceleration that she is experiencing. And then so now we'll just draw a dot to represent the softball player in our force diagram. And then like before, we'll do the most basic thing, which is we'll put a downward arrow to represent force gravity. And so it's force gravity on the player by the earth. And then the same thing as last time, well, there is in fact a normal force on this, since there's once again no other thing that would cause an upward force on this player. So we'll draw force normal, and then it'll be on the player by the ground. And then, so now we have to address this net force, because this net force is pointing in the left direction. It's not pointing up or down. So we know that the upward forces and the downward forces have to be equal, but there is an unequal force towards the leftward direction. So what is this? So when we're looking at this picture, we can see that, well, she's sliding onto the base. And in the question itself, it doesn't say that there isn't any friction. It doesn't say that it's frictionless like the last question did. So we can assume, right, that in this case there will be friction. Additionally, friction is a force that acts in the opposite direction of the motion, which lines up with what we have here, where the net force is in the opposite direction of the softball player's motion. So that all lines up. So from this, we can infer that the leftward net force is caused by friction. So draw our leftward arrow in, and then we'll write kinetic friction. That's what the FK stands for. That's Okay, technically that's friction kinetic, but that just shows you that it's friction first, and then the type of friction is kinetic. It's kinetic because the software player is moving. If it was staying still, then you would write static friction, right? So this is a kinetic friction on the player by the ground. Alright, so finally what we have to do is the equality markers. So just like before, the vertical net force is 0. So from that we can infer that the force normal and force gravity is the same force, just in just in opposite directions. So we'll just draw equality markers on the two of them, and that'll be that. So for our final question. So this question is going to be a little bit interesting because there's a pull on the sled at an angle. So that kind of shakes out our force diagram a bit. So first we'll just draw a circle around the sled and the kids. And then, well, what's on that force? Well, in this question, it doesn't say that it's accelerating, and it says decelerating. From the picture, we can't tell whether it's accelerating or decelerating. So we'll just say for now that it's either at constant speed or it's at rest. So we'll say net force is 0 for this question. And then we'll put in a dot to represent the force on the kids and a force diagram like usual. And again, do our most basic thing. This will be the first step for any force diagram problem, is that we'll just draw in force gravity. So a long downward arrow with force gravity acting on the sled by the earth. Okay, and then so here's the tricky part. So we'll start first with the pull of the sled at an angle, because that will help us infer the rest of our forces. Because the rest of our forces are all reactionary forces, but they aren't, they're not active forces themselves. So, but we know that this pull on the sled is definitely there. It's definitely at an angle, so that will be the easiest thing for us to draw for now. So we'll put in the force at an angle. We'll draw the arrow at an angle. And what force is this? Well, it's being pulled by what looks to be a string. And what strings mean in force diagrams or forces in general is that there's usually tension in the string that would pull the sled in some way. So this is force tension, and it's on the sled, and it's exerted by the person, this guy pulling the sled. So then after that, well, let's take a look at well, the net force is 0, so we have to somehow balance out this angular force. So let's take a look at the horizontal forces first. So we're gonna split this tension force into the vertical component and the horizontal component. Okay, so that just means that in this force, this is where this is the horizontal force that it exerts if you had to break it down, and this will be the vertical force. These forces itself aren't actual forces. It's just a simpler way of understanding this angular force. So once we break it down, we can see that the horizontal force of it is about this long, and so there needs to be a force in the opposite direction of about that much as well. So we'll just draw the arrow first, and then let's see what can account for this force. Well, again, in this question, it doesn't say that anything is frictionless, so we can assume that there is friction between the sled and the ground. So we'll write force and then kinetic friction, again, because if this vehicle is moving. If it's not moving, then once again you write static friction, but we'll write force kinetic friction on the sled by the ground. Okay, so that'll be our the first force that we figured out. So that balances out the horizontal force. The horizontal net force is now 0. So now we'll look at the vertical force. Currently, with this situation, the vertical force would be unbalanced because there's more force gravity than there is of the vertical component of this force tension. So we'll need to balance that out somehow. Now, in our past problems, we'd usually solve the vertical force with force normal, and today is no exception. So but to calculate force normal, it's not our usual force normal where the normal force is equal to the gravitational force, because there is this tension force that brings in an additional vertical component. So this vertical component is moving is a force in an upward direction. So we can already tell that will account for a bit of the force gravity, about this much in fact. So now we can see that our force normal will have to be equal to the remainder of the gravitational force. So it'll be shorter than the usual normal force by the vertical component force of the tension force. So we'll draw in the shorter arrow at the top, and then we'll label that force normal on the sled by the ground, because once again that is a surface that the ground is traveling on. Now this step isn't always necessary. It's it's for your help really, which is the equality markers. Now, as you look at this diagram, nothing here is really equal. There's none of the lengths of any of these forces are equal. They're all going in different directions. However, you will notice that the horizontal force of the kinetic friction and the horizontal component of the force tension is equal. Those are the only forces on either side, and the net force is 0, which means that they must be equal. So you can draw equality marks on the kinetic friction force and on the horizontal component of the tension force. However, none of the other vertical components would fit into this, because the vertical components, there's more than just one force acting there, and they're all at different values. So you can tell that it's not going to be equal no matter what. So those equality markers. Now, on an actual test, this won't be necessary because because, as I've said earlier, the horizontal force of the tension force isn't an actual real force. It's just there to help you understand better the different components of this angular force, because otherwise we don't know how to deal with it, right? Because it's not on the normal x and y axis. So on an actual test, you don't have to draw in the equality marks for the kinetic friction force and for the horizontal component of the tension force, but that would just be helpful in this scenario. So, all right, that's the 3 questions that you'll face in worksheet 1. And so, if you still have any questions regarding these problems, or if you have any confusion, you can submit a comment in the poll that I have in the description below. Or additionally, if you want to ask for some kind of change in these videos, like you want a different kind of style in them, then you can also suggest that in the form below. Thanks for watching!